Good day and welcome to our class. Today we want to talk about Riemann stages integral. So we have considered Riemann integral in our last classes. So we want to consider Riemann stages integral. Before that, we need to consider the definitions. So we have the definitions here. So we start by this. Let g of x be a monotonic increasing function on this closed interval AB. And what do we mean by monotonic function? We mean a function that is either increasing or decreasing. So for instance, if you have this interval 1 to 5, this interval 1 to 5, let's say this will be 1, 2, 3, 4, 5. Let us just pick these numbers. So if I pick s squared now, for every value of x, this is 1, when s is 2, this is 4, when s is 3, we have 9, you have 16, when s is 5, you have 25. You see that for all these values of s, this thing is increasing. So we say that this function is monotonic increasing in this interval, or simply it is monotonic. So that's why I say let g of s be a monotonic increasing function in this interval, and let P be any partition on this. Then we define this thing delta gr to be g of sr minus g of sr minus 1. Here we say that it's greater than or equal to 0. Why? Because g is an increasing function. Definitely this one will be higher than this one, and this minus this will be greater than or equal to 0. So we do not want to know what is there, but since this one is higher, so it will be greater than or equal to 0. So we now say that let f of x be a bounded function defined on the same interval. So this is if you still remember this is upper double sum for Riemann stages integral, and this is lower double sum for Riemann stages integral. So what Riemann integral only did is when we have this type of integration, f of s d of s. But what Riemann stages integral did was this: f of s d of g of instead of d of s. Example, if you have, let's say, a function like this, sin s d cos x instead of the ordinary x. So this is this is the idea of Riemann stages integral. So we first define the upper Riemann stages integral of f of s to be this. So it looks like that of Riemann integral. Is the same idea. So that is the infimum of upper double sum for Riemann stages integral, and this is supremum of the lower double sum of Riemann stages integral. So most of the things we did under Riemann integral is also applicable for Riemann stages integral. So, and as the same thing we have under Riemann integral, when this upper and lower Riemann stages integral are equal, then we say that the function is Riemann stages integrable over this g of s. So when these two are equal, so we say that this is Riemann stages integrable. So now we first take care of this. Let's take this example. We want to evaluate this by using Riemann stages integral definition on this interval 0 to 1. So we have an example here. This is the example that we spelled out the other time. So if you look at it, you see that f of s is x here, g of x is s squared. So without stressing ourselves, you will all know that g of x is monotonic increasing in this interval. So I have told you how we can know that a function is monotonic increasing. So see an example that I gave here. That is, whatever value we put here, the value will be the value of this function will be increasing. So that simply means that this function is monotonic in this interval 0, 1. And also, if you look at f of s too, f of s is bounded as well. It's bounded in the same interval, because same thing when we put s to be 0, you are going to have 0. When we put s to be 1, you are going to have 1. So that simply means f of 0 is less than or equal to f of s. It's less than or equal to f of 1. So it has a supremum and infimum. So it is bounded. So since it satisfies these two, therefore f of s is Riemann Stieltjes integrable over this g of s. So let's keep that. So we have seen that it is Riemann Stieltjes integrable, but we need to find the value of this. Now, how do we start that? So we'll consider a partition. So let P be any partition on this 0, 1. So we know that H is equal to B minus A over N. Our B is 1 as usual. Our A is 0 over N, which is 1 over N. So we can now write our partition in this format. You can see, as usual, you can say R minus 1 over N. That is R minus 1 times this. R over R times 1 over N. So this is a partition. So R is 1 to N. So we can write our partition like this. So let's keep that. So we need to know about g of s, the g, because of definition. We need to know this, the g of r. The g of r simply means s of r minus g of sr minus 1. Now, what is now g of r? G of r means anywhere I see x, I should put the supremum in anywhere I see s in this g. This is g. I should put this supremum. You know, SR is the highest. This is SR. This is SR minus 1. So anywhere I see her. So in this place now, this thing will just be R over N. That is our x, all square, because there is square there. Whatever thing that is there, that is what you are going to follow. Just replace s by this one. This is SR minus 1. That is this one. You know what we have here is minus. This is TS. Anywhere you see s, put this one there. R minus 1 over N, all squared. So from that place, it will be very easy for me to simplify from here. So by the time we simplify this, we should be able to have 2r minus 1 over n squared. So it is very easy to do. Now let's keep that. So we have known this. So we need to know the big MR, and we know that the big MR is the supremum of f of x. Now this is supremum of f of x. That is, anywhere we see x in our f of x, we put this supremum there. So this about our f of x is ordinary s. So big M is just r over n, and small m is the infimum. This is infimum. So, but it is ordinary s, so I don't need to stress myself. So it is just r minus 1 over n. Assuming it is square like this, I'll just put square, but it is ordinary x in this place. So from that place, I can now calculate the upper Riemann Stieltjes integral, which is this. So we have given it before in the definition, and that is, but remember we put infimum there, but we have proven all this in our Riemann integral to be limit n tends to infinity. So this is summation r runs from 1 to n. The big MR is r over n, Why this one, which is this, is same thing as 2r minus 1. So I'll just put it there to be 2r minus 1 over n squared. Now, by the time I simplify for, so we should be able to have this 1 over n cube. This is n times this n cube. If you expand this, this is 2r minus 1. There is 2r squared minus 2r. By the time we expand this r, but don't forget we have done this before. This is sum of r squared. So it will just give you, this is the 2 here, but this sum of r squared will give you this, minus sum of r. You have done this before, I've given you, it will become this. So I have n cube here. I'll first divide one of this n cube by this n. It will remain n squared. So this is gone. So the remaining n squared, I shared it under these two. By the time I use it to divide this one, I will have 1. I will have 1 over n. By the time I use to divide this one, I will have 2 plus 1 over n. The same thing goes to this. You know, 1, and this n has cancelled one of these n cube. It will remain n squared. So, it is under. That's why we have 1 over 2n, the first n squared. The second one is being divided by this. This is 1 plus 1 over n. So, an ascent tends to infinity, the whole of this becomes 0. This is 0, this is 0. All of this will be 0. That is why we have this. So, by the time we simplify, we get 2 over 3. Now, that is for the upper Riemann integral. For the lower Riemann Stieltjes integral, f the g. So we know that that one is this. That is the small m r. But we know that our small m r, this is it, r minus 1 over n, and this is our the g, this. So this will be r minus 1 over n. We just put it there. The g is 2r minus 1 over n. So this is over n squared. So by the time we simplify, we should be able to have this. So this is n and n squared. It is here. If you expand this, r minus 1 and this, we have this. So it has led to the idea. We know what 2r squared is, which is this. This is r squared. You know what ordinary r is. This is ordinary r. An ordinary one in summation, we know that one is n. So writing everything out, we should be able to have this. So you observe that this is just what we had there. So it's the same thing. This one at the end of it will give me 0. You know, this one, by the time we divide both sides by the time we divide this thing by n, it will remain 1 over n squared. And as n tends to infinity, it will also be 0. This will be 0. It's just like this one too. So what we are going to have left is just 2 over 3. So that means the upper and lower Riemann Stieltjes integral are equal. So this one also shows that the function is Riemann Stieltjes integrable. And we can conclude, we can just conclude that therefore 0 to 1 x the s squared is 2 over 3. So that is that about that. So let's take another example on this. So I have another question here. Evaluate this integral f of s dg, where f of s is s squared, g of s is s squared, using Riemann Stieltjes integral definition. So solution, I will not need to do everything here. It's just a clue. So we should know that f of s squared is bounded, and g of s, this is f of s squared, is bounded, and g of s squared, we have shown the other time that is monotonic increasing. So and it is, you will see yourself, you can try it, that is monotonic increasing in this interval. So in that case, satisfies Riemann Stieltjes integral definition. So the next thing is just consider a partition P. So let P be a partition. Then we know that H is equal to B minus A over N. But this is B. A is 2. Sorry, A is 0 and this is N, 2 over N. So we can now conclude our partition is R minus 1 times this. That is it, comma R times this. That is 2R over N. So R runs from 1 to N. So we have known our partition. So this will always be our infimum and this will be our supremum. So that's the short form of our partition. Now the next thing is we need to get our the GR. The GR, which is the SR minus the SR minus 1. This one, SR is the supremum here. This is our SR. So that is anywhere we see X inside G. This is our G. We put this thing there. So that is 2R over N, but there is square on top of that. Minus, this is our SR minus 1. 2R minus 1 over N, all squared. But it is easy to simplify here. By the time we simplify, we should be able to have what we had the other time over N squared. So by the time we simplify, so that is that about that. So it remains capital letter MR. Capital letter MR, that is supremum of f of x. This is sup f of x in that partition. Now this is supremum. This is supremum. That is anywhere we see x inside f, we put this. But our f, we need to consider what is there. Our f is s squared. So this is just 2R over N all squared. The other time is just ordinary f, ordinary x, but there is square on it now. So this is just 4R squared over N squared. So finally, small mr is infimum f of s. So this is 2R minus 1 over N all squared. So this is the infimum. So this one will just be 4 into R minus 1 square over N square. So it is easy for me to do from this place. So we can now have upper Riemann Stieltjes integral to be this. I'll just need to put those things that I've got. This is our big MR. This is our the GR. I'll put it there. So the only encounter you are going to make here is just summation R raised to power 4. Summation R raised to power 3. So that is the only encounter you will make there. And I've also given you. So this is just that is R runs from 1 to N. So this will this will give me N squared plus N plus 1 all squared over 4. So that is for the cube. So you take the limit as n tends to infinity. So you should be able to get it. So that should be left as exercise. So you go and do that yourself. So that is that about that. So we have another question there. If f is bounded on this and c is constant, then let us evaluate integral f dc. So without stressing ourselves, we should know that the answer will be 0 because differentiation of a constant is 0. But let's use Riemann Stieltjes integral definition. So I can use instead of upper double sum that I've been using, I can as well use this Riemann sum definition. So it's just for upper sum we normally use capital M and small m. For the Riemann sum we use this. So we say that T belongs to SR minus 1 comma SR. Now from this place we know that R minus 1 this. I don't want to know what this one will give me. I don't want to know because it is not specified. We only told that f is a bounded function. Now the g of R, but we know the g of R to be SR minus 1 SR this So which at the end of the day, but since f is constant, the supremum and infimum is still c. Since g is constant. Sorry, okay. You know that this the c. The c here means the g. That is, g is constant. So since g is constant, so this g is our c that is given here. You know, we normally write f dg. So this is our g. Since g is constant, the supremum and infimum are the same thing. So this thing is just c. They are the same since it's constant. So it has no any workings. It is just c and c. They are the same thing. So this is 0. So since we get 0, we can conclude that therefore integral a to b f of s dc be 0. So if we make use of the upper double sum, it's still the same thing. But the supremum and infimum of g is still the same thing because g is constant.